I think we reached out to a lot of the.
Okay. Wait.
Yeah, one. But I think it's not, otherwise it's not. I mean, the one that I talked to. Yeah.
Okay, everyone. Are we ready to start? Is everyone here? So, welcome everyone. Today we're extremely fortunate to have Aghil Alaee, who's just had a second child, so he's extremely busy. I think of Aghil as an academic older brother. When I first came to the BHI, he was extremely welcoming. I spent many hours in his office at the very beginning. We even wrote multiple papers together, of which I'm still very, very happy. And it's all thanks to your generosity and your skill in proving all kinds of lovely geometric inequalities. But anyway, today it's a slightly different direction, I believe. We're talking about existence of apparent horizons and size of extra dimensions. So Aghil, take it away. And thank you for joining us.
Hello, everyone. First, I want to thank you.
Okay, speak a bit louder.
Okay, thank you. First, I want to thank you, the organizers, for the invitation and the opportunity to come to my work. So, yeah, we'll talk about the existence of apparent horizon and its application to the size of extra dimension. So this talk has two parts. The first part I will talk about some recent results on the existence of apparent horizon. And the second part, we try to apply this to answer an interesting question, at least for us. We found it fascinating. That is there any threshold for the size of the extra dimension? It's really big, and then you can ask the question: is there a threshold for the size of that extra dimension? So let's just start with a very classical and beautiful picture by Pedro. In 1972, Thorne actually studied, non-spherical symmetric gravitational collapse, and this was a paper dedicated to the 60th birthday of John Miller. So in this paper, he actually derived the conjecture about formation of black holes, and the conjecture in his own words are, is as follows. Event horizons form then and only then. A mass m gets compacted into a region whose circumference in every direction is approximately less than or equal to 4 pi gm divided by c squared. So the conjecture, yeah. So that's it. That's the thing I will talk about. So mathematically, the conjecture is not very rigorous, and I will talk about that. One of the questions is, what is that mass? Okay. So to put that, in his own, words, after this conjecture, the sentence after that is like most conjecture. This one is sufficiently vague, leaving room for many different mathematical formations. So the question is how we can make it first precise and what we can prove mathematically. So the first part is about the event horizon in this statement. So the event horizon, if you have a black hole, event horizon is a black hole, is the boundary of black hole region. So right, you see a picture of the Carpenter-Penrose diagram of gravitational collapse, and you see the singularity, and you see the event horizon. This is the event horizon, and this is phi plus and this phi minus. Now, event horizon, by just looking at this picture and looking at the definition, the boundary of the black hole region, it's a global property of space-time. So it's not something local that we can characterize it locally. So it's a global property of space-time, and when you have a region, you need to change the notion of horizon, something that you can mathematically characterize. Okay.
Pardon me, Aghil, but just because it's something that some friends of mine and I have been talking about recently, can you tell me what you mean by locally here?
Oh, locally means, okay, here, let's say, select the hypersurface at constant time, the slice of the space-time, the compact domain, and this is the picture of that. This is physics. And this is the boundary of that. So as you can see, this picture, this hypersurface only have a cross section of the line. So can you, if you select the surface, can you actually detect the geometry of the event horizon just looking at the cross section of that? It's impossible. You need to know the full evolution of the initial data set. You need to know the complete structure of the ascribed loss, and that means you need to have a proof of the big cosmic censorship matrix. That's it. The ascribed loss is complete and the singularity is behind black. So it's impossible if you're sitting here in this domain. It's impossible to detect this cross section. Okay, and it's not possible to mathematically characterize it. To figure out what is their structure, you need to see the full picture and then look at that. Okay, this is their I need to go to the infinite time and then say this is their. The other part is, as you asked, what is the mass? So there's a definition there about the mass. What is the mass? Is the proper definition of mass in the conjecture. The next one is what is the proper notion of size of that region. So how to measure this compact region. And the next one is there is a physical constant there, and what is that physical constant? Okay, what's the precise physical constant? If you can't even find it.
Just a little figure on Eric's question. One way to reformulate what Aghil is saying is that if I give you an S2 and I give you an induced metric and I give you a mean curvature, that's the data that you have to work with. And now I ask you the question. I say, is it a cross section of the horizon? You won't be able to know from that.
Yeah. You need to go to the infinite time, and then you will be able. This is them. You don't go to the infinite time. You're not sure where's the horizon. Okay, to answer this question, we need to go to the framework of GR. Framework of GR is Einstein equations. It's, if you fix a gauge condition, it's actually a system of quasi-linear hyperbolic PDE. And it's beautiful because we know a fundamental result about that from Chocobo and Perosh, and it's a well-posed problem as an initial value problem. So if you know the initial condition, you can solve it at least locally. And that's you find a unique maximum extension. So as a result, in many problems in GR, including geometric inequality, which was the book conjecture, it is not necessary to know the knowledge of the entire space-time. You can only focus on the initial data set. So if I have a space-time, let's say M3, M1, and G4, which is a solution of the Einstein equation. So we look at the constant. This is constant time hypersurface. So let's say T equals C, and then it's a space-like surface, and that means the normal vector here, it's time-like. What information you have, if this is the space-time, you will have the manifold, the metric, and the extrinsic curvature. The manifold will tell you about the topology and geometry of this hypersurface. G will tell you how to measure angle, size, and the curvature, so intrinsic geometry of this hypersurface. And K will tell you how you actually put this hypersurface in the ambient space. So it will tell you extrinsic curvature. But we know from geometry that if you have a hypersurface of a semi-Riemannian manifold, there is a relation between the curvature, and it's called the Gauss-Pedatsky equation. And if you take the trace of the Gauss equation, you will find some constraint. So you cannot take any triple like this. The triple should be a solution of Hamilton and constraint equation. The first equation is called the up equation, and the second one is the moment constraint equation. And the left-hand side mu is the energy density. So it's like T of n at n, and the J is the momentum density. It's T of n, and it's a vector. So you can select your vector and find the energy momentum density. Sorry, the momentum density declaration. Okay. So up to here, we have our initial data set, but in GR, we don't look at any solution of the Einstein equation. We should look at the solution of Einstein equation which are physically relevant. And that means you need to impose the energy condition. So usually all relativistic matter in the universe, they have the dominant energy condition, and that's the one you pick. And then you translate that to the initial, in the level of initial data set, it will be equivalent to mu bigger than equal to the normal of J. Okay, so we take this triple with this condition. Okay. Now note that if I put k equals 0 in these equations, this part will be trivial. So J will be 0, and this will be 0, and this part will be 0, and we will end up with a scalar curvature proportional to mu, and we know mu is bigger than J, so it was scalar curvature non-negative. Okay, so mathematically, this is the tie between GR and geometric analysis, because in geometric analysis, we are very interested to characterize and classify object based on the geometric structure and logical structure. And the way we do that, it prescribes some curvature condition, or reaching curvature lower bound, scalar curvature lower bound. If we know these, we can actually classify these spaces. So that's a tie here. And as a result, there's a deep connection between these two things. Now, what about the horizon? So if you have a hypersurface of your space-time, you can talk about a region and then say that region, let's say this region is a region inside black hole, to actually in the level of a space-time to see what is the characteristic of surfaces here. Actually, if you select the surface, we call this surface a trap surface, which is inside black hole. If the null expansion, in the outward direction, which is L plus, it actually the expansion is negative. Okay. So usually, if this is a two-dimensional hypersurface of your space-time, the normal bundle, it's a Lorentzian, so you have two null direction. One of them is outward, and another one is inward. You always expect the inward one, the expansion to be negative, and that surface gets smaller and smaller. What you expect, if you are the usual, hypersurface, the outward expansion, the area gets larger and larger. But if it is inside black hole, then it's trapped. So the thing that happened, something like this show up, and because the theta plus is negative, the area will locally decrease. Okay. So the boundary of all of these trap surfaces is called apparent horizon, and that's a case that theta plus is equal to 0, but that means the mean curvature of this hypersurface sigma plus the trace of a k with respect to sigma should be 0. So these two this is just theta plus. Okay, so we can characterize a notion of horizon in the level of initial data. So if you put k equals 0, we'll go to the time symmetric case. That's a minimal surface. The minimal surface are beautiful objects, and the reason is they are like geodesic, which is the critical point of arc length. Here, the minimal surfaces are critical points of area functional. So there are fundamental in geometry, and one of the famous example is Sophia. Okay, it's a minimal surface.
I'm sorry, one of the examples.
Sophia. Yeah. Now, the nice thing about these surfaces is we have a fundamental theorem. It's a Penrose singularity theorem, and can you recall the Penrose singularity theorem? If you have trap surfaces or mods or apparent horizon, then you know the space-time is not geodesically complete, and as a result, there's a notion of singularity. So there's a conjugate point. You start from a point here, and you find there will be a conjugate point. This conjugate point represents the singularity, but the singularity notion of singularity is not very strong, so it's not a curvature singularity. The curvature does not break down, but only the geodesic actually their focus. So as a result, we can get the singularity. Now, if you assume the big cosmic censorship is whole and it's a theorem, then any singularity is behind black hole. So we actually found that. Finding the apparent horizon, mathematically assuming the big cosmic censorship hold, it's a proof for the existence of black hole. Okay, let's look at the one of the fundamental results in this direction. Is a result.
I missed something there. Why do you need the big cosmic censorship? Isn't the convergence already telling you that you've got singularity?
Now, how do you know you have a black hole? The singularity may be naked singularity. You have a black hole. The singularity is behind the black hole. For that, you need a full evolution. You need full, complete the structure of the Stratosphere, and that means you need to prove the big cosmic censorship.
So far you only have the apparent horizon. Now you're saying with also the weak cosmic censorship, it's a real event horizon.
Yes.
Thank you.
It is you have there's a black hole, and there's exists event horizon. Maybe it's not this one because apparent horizon sometimes are inside event horizon, sometimes are outside event horizon. Yeah. But because that. So Shane and Yao, they actually event horizon.
Say that horizon.
It's a theorem that they're not. Yeah. I think you just if you have a mods, it has to lie inside.
What about the dynamical setting? There's like a strong matter which comes.
No, that's horizon. That's Penrose's.
Okay.
Yeah.
Thank you for
Sure.
Yeah, thank you. So let's look at the one of the fundamental conjecture, the fundamental theorem about the proof conjecture. It's by Shane and Yao, 1983. So after they proved the positive mass theorem, they noticed that they can apply the technique to prove the hoop conjecture. So let's take a compact domain. This is our compact domain, like omega, G, and K. So we have an initial data set, and assume the boundary is untrapped, and mathematically, and assume something a bit stronger, and that's a condition they put here. It's a technical condition to show a system of differential equation has a solution. Assume this condition on the boundary. Sigma is the boundary. Assume this condition, and also assume that the mu minus j is strictly positive, as long as the square root of this quantity is bigger than the square root of 2/2 times pi over the radius, then there exists an apparent horizon inside. So they prove the existence of an apparent horizon. There's an apparent horizon.
Can you give a sense of what the matter that might be if it's a J is like?
So you can in the constraint equation you can put different matter in the Einstein equation. Matter or any other type of matter.
Which are like Casimir energy that negative A compared to.
As long you need a notion of dominant energy. So I don't know if this type of matter they have this kind of notion of dominant.
So yeah, so something you this is something you want to make a wormhole. So this is.
I don't think so because you need this dominant energy to have this formation. Oh, kappa was right here. Kappa is like 8 pi g over c the physical constant.
I see. You just make.
Yeah, that's the minimum assumption. But if you have this condition, then you have that otherwise. That's like saying has a strict dominant.
Am I understanding this right? If you don't assume that d omega is you drop the condition d omega you still have a black hole.
Yeah. So the thing
It's
is,
just you wouldn't have an apparent horizon because your surface.
yeah. So the first of all, you want to have a surface outside the horizon, and then say there is something inside.
So if you just want to
So-
talk about the conditions for a black hole,
Mathematically, here this is a technical assumption. They need that.
So yeah, the
But,
way.
but on the other hand,
there's the boundaries where you want to prove not that it's a space-time.
You can't prove that with this. This is saying I give you a surface that's sufficiently far in a region that's untrapped, that's totally fine. And then this is just a theorem that gives you a relationship between the lower bound on mu minus j and the size of the region for which this lower bound holds, in order to infer that somewhere inside, but you're agnostic about exactly where it is, somewhere inside lies a MOTS.
Yeah. You want your surface which you're sitting on, let's say you're here, you want to be outside the black hole, and the question is, can you detect something inside that? Yeah, you can move the surface inside also, and ask that, okay, is this surface inside black hole? So you cannot be mistaken. That's the theorem doesn't. Yeah.
One of the interesting things about the statement here is the scaling. So
You want to check whether it's everywhere.
yes,
Yes.
Yes.
Income everywhere. Strictly. It's strictly positive. Yeah. So this doesn't work for the vacuum. Let's say you have a vacuum. You should take some.
Is it same as minus j?
Yeah, it's the same.
Yeah.
It's the same.
Yeah.
Why do you write?
Because sometimes, so you have a function, so sometimes the infimum is so sometimes the infimum, let's say you have this open interval 0 to 1. So you say this open interval has a maximum and minimum, but the maximum and minimum are not inside here, are 0 and 1. So there are supremum and infimum. Supremum and infimum are the upper bound and lower bound, but infimum is the largest lower bound. Possibly it can be, in this case, it's not inside the set, but for here, so here, infimum is 0, but it's not inside the set, but here the infimum is 0, and it's inside the set.
You're saying it's not just greater than 0 everywhere, it's actually bounded away from 0.
Yeah. So let's look at the theorem. The theorem, I did not say what is the radius. The radius is actually a very complicated radius. So the radius, intuitively, you can say it's the radius of the largest torus. You can embed it there in the domain. So it's hard to compute. That's one of the difficulties in the theorem. The other difficulty is if you assume the trace of k is very small. 0 is very, very small. The theorem does not. You need to have trace of k, non-zero or large.
So the radius is not the largest radius of the largest apparent horizon.
So the radius, let's say this is like a sphere, yeah. It's not like this far. It actually it's this. I put the torus here and I fatten the torus up to this. It's a donut. It's a very fat donut, and the radius will be this one, which is like r over 2. their radius, omega, it's actually R over 2. You have just this view.
So it's a very it's a complicated notion. It's very hard to compute for
Yeah.
anything outside of spherical
Yes,
symmetry.
very simple.
It's extremely hard to compute. It's just it's a quantity that ends up being exactly good enough for the proof.
And actually, it makes sense in the sense that, okay, what is the Hooke conjecture? So, Kip Thorne, you start to study, almost like a ellipsoid, plane, and then you look at like a circle and look at the circumference of that, and you look at the thing that if the circumference of the circle in all directions, if you just put it, you should try it in all directions less than some like 4 pi g m divided by c squared, then there will be a. So this is playing the same role. The way they construct this radius, they take a circle and they fatten the circle. As long as this fattened circle will give you a torus, as long as it does not, bound a disk. So that means a fatted circle until these two regions actually hit, but does not form a disk.
So this radius is going to depend on what metric tensor you use.
Yeah. The radius
Yeah.
depends on doing it, definitely.
Yeah.
I mean, looks very porous.
And you expect it to be the case. You expect it to be something complicated, because if you go to a complicated domain, you expect a complicated notion of radius, but you want something that you also be able to compute. If I give you the metric, you cannot compute this. It's harder. Okay. Now there are like many other works in special cases try to have a kind of a better, nicer look theorem. For that, they impose extra assumptions like spherical symmetry, maximal slicing, axial symmetry, component flat geometry, and they derive the same sort of result, but they have a strong assumptions in the initial data set. Also, there is existence of minimal surfaces in the case that k is equal to 0, using a quasi-local mass. So the mass they use to borrow your quasi-local mass, and this was a beautiful paper by Shi and Tam, and recently with Martin and Professor Yao, we extend the result to the existence of apparent horizon using more general quasi-local masses like Lim Yao and Wang Yao quasi-local masses. So there are other results, and there is also a dynamical. There are actually dynamical results in this direction, and it's actually initiated by work of Christodoulou. He produced sufficient condition for existence of trap surface using radiation, and his initial paper was in 1992 using the spherical symmetry, and later in 2008 he proved the same theorem without assuming any symmetric condition. But this work also generalized to different cases, including the work of Martin. And really, if you have any question regarding dynamical setting, ask Martin. So what we have here, so we want to address the first two comments or remark. The first one is the radius, the second one is the small trace of k. For that, we look at a class of initial data set, we call that admissible class. And that is not very strange condition. It's the condition is it says that, okay, take an initial data set, take a triple, and assume that the Ricci curvature, diameter, and the second fundamental form plus the mean curvature of the boundary and the Gauss curvature of the boundary are all of them are bounded. So they don't have a behavior, unbounded behavior. Okay. So you can have a function like, let's say, 1 over x, or this interval 0 to 1 is the smallest you can differentiate it, but it's not bounded. So we are looking at the case that they are bounded. And call this admissible class by fixing these bounds. Okay. Now our result is as follows. So this is a joint work with Yao, and this work is in progress, and I would say which part we need to address. So the result is as follows: select the initial data set in that visible class. For each, set of these parameters, C, H, K, and R, for each set of these constant, you can find a dimensionless constant such that the same type of inequality that Shane and Yao, had, actually is whole, then there exists the apparent horizon. The difference is there is no complicated radius. It's a volume which you can easily compute. It's a radius of the boundary you can easily compute. The only part is C naught. So C naught is the one that it's very complicated to actually write it down. It's related to a solution of a differential equation. And we are currently working to estimate that in special cases, like in the spherical symmetry, and when you have a maximal slicing. Yes.
So I think the original loop conjecture had this greater than or approximately equal to.
Yeah.
And there's presumably some constant that's supposed to be close to 1. Probably not exact. So is it that C that's going to turn into that quantity?
So the thing is, in the original conjecture, the mass is something that we need to determine. The size is something that we need to determine, and the constant is something that we.
And the constant should be about 1.
No, we don't know what is the constant.
But there's something that makes something like less than or it's like greater than approximately equal. That.
No, we don't know what is the constant, and the thing is, when you fix the notion of your size, fix the notion of the mass, then the constant will change according to that. So in each, maybe your notion of the mass has a constant in front of that, so the constant should change every time when you change the notion of size.
So there's no like quantitative way that this approximately equal to is going to come out with a constant that is close to some other.
No, we don't know what is that.
I think in some settings and under some assumptions,
Yeah.
you can find a constant that works,
Spherical symmetry, let's say.
but there's no universal constant that applies for all definitions of mass and size, etc.
If you change your domain and then you expect the constant to change, and the way you measuring the mass, if change, the constant should again change. So it's everything are part of the problem to find out. So this result is nice because the volume is complete, but still this result does not work when the trace of K is very small. So we came up with something complicated, like the Shane and Yao, and we defined a notion of volume. We call that the harmonic volume. So the harmonic volume, it's actually depends on the function how, depends on the domain and the metric, and also depends on the solution of a differential equation. So this is very technical. I will not go deep in this, but what I want to say is you may think that, okay, you have something positive like here, but the infimum can be 0. You're taking the infimum, okay? The infimum of this term is 0. But we can prove that the infimum is not 0. But we can prove that the infimum, if you have a domain which is, it has dominant condition and the boundary of the domain has a positive dose curvature and positive mean curvature, then this is a positive constant. Okay, that's the part that mathematically we can prove.
So you're solving A is the set of solutions to this PDE with these assumptions.
Yeah, so the thing is that we last time I think.
So it's like the Laplacian on omega tilde omega plus, and the boundary condition is f equals tau on the boundary of omega.
So take a domain like this, Martin, and this is your domain. Now multiply by r. You take a graph of this domain. Now look at and extend this in a very special case. You get asymptotically flat. Okay? Now you have asymptotically flat manifold. Far away, it's flat. X goes to infinity. G approaches to the flat. Now solve this equation. solve a harmonic function. But you need to impose some boundary condition, assume u to be x or y or z, one of these coordinate functions. Solve it, and you will have a u. You know the existence of solution. And then take the infimum of all of these possibilities. There are many cases for f, and each f leads to different u.
What's the last condition?
Oh, so the extension is not arbitrary extension. It's the extension that you can construct based on the result of Miao and Xi. And the extension is such that the mass of the extension, so this is the extension, this part from here to there, it has the scalar curvature 0. And the mass of the extension, the ADM mass of the extension, is strictly less than the area of the boundary or system. This type of extension you can construct.
Sure.
If you have positive curvature and positive curvature.
Why that constraint of the mass?
Oh, you need this because in the proof we are using it. So in the at some place in the proof we are using this one. Okay. Using that, you can get the following. So the same sort of matter content that Shane and Yao has. If you have an initial data set, so boundary again is untrapped, and the Gauss curvature is positive. Then if the matter content is bigger than some notion of the initial notion of the area of the boundary divided by its harmonic volume, assuming tau is equal to 0 at the boundary, then there is a set unbounded ones. Note that again, the notion of size is here. You can call this constant to be constant, or you can look at that as a notion of volume. Either case works, but this is a dimension constant.
Again,
The result is called volume.
again, it's very pretty, the result, but can you give us some kind of physical intuition as to why the assumptions that you put on the solution to the PDE is somehow tracking something? Is there some intuition behind those choices? Or is it just like we did the inequalities, that's what we needed? But is there some extra story?
So let me say the extra story is this. Recently, like a year ago, a mathematician, they found a new proof of the positive mass theorem. And the new proof of the positive mass theorem is related to this harmonic functions. So if you have a harmonic function with this property, you can prove the positive mass theorem. And this was a beautiful observation because there is a deep tie between this technique and the spinora proof of the data. Okay. Now, our hope was to use the new proof and prove the Hooke conjecture, the same approach that Shane and Yao used. And the hope was the new proof will lead to a better constant. Okay. If we try that, it's lead to a complicated constant, but still we need to estimate. The nice thing about this is it's a PDE, so we can use technique in the PDE and hope that in some special cases we can estimate. Okay? In the case of Shane and Yao, the definition of the radius, it's a complicated, geometrical definition. You don't have analytical technique to estimate.
I see.
That was our mindset.
Right. So you switch the right-hand side to something that you could actually estimate
Yeah.
using analytic means.
Yeah.
As opposed to something completely nonlinear that you don't know.
That's a goal.
Okay, that's the goal. Yeah. Okay.
And another nice thing is you can have existence of minimal surfaces. This did not work in the case of Shane and Yao. They could not get the existence of minimal surfaces. I need to say this theorem, it's geometrically it's very beautiful because there's no result in the literature that says if there's scalar curvature of a domain at some region is very large, then there is a minimal surface. But this result actually says that. So it says if you have a manifold, if the boundary has positive Gauss curvature and mean curvature, take an arbitrary function, which is not 0, on the boundary, and take a epsilon sufficiently small. Then, as long as the minimum of R is bigger than this expression in terms of the harmonic volume area of the boundary and the function tau, then you have the existence of minimal surface. So this will address the time symmetric case too.
So how does epsilon feature? What does it depend on?
So epsilon is sufficiently small.
But it doesn't depend on the initial,
No.
it's just some constant that's just big enough to give you room in the inequality.
No. It's a constant that actually you can make it as small as you want until you get this condition. It's a constant cannot be zero, but it can be very, very small.
Okay, but there's no choice that I have. Like I could just take any epsilon sufficiently small.
And if the scalar chart is so about, then you have. Okay, let's. What's the definition?
H equals 0. The
Oh,
mean
H equal, the
curvature
mean
equals
curvature is
0.
equal to 0. So it's like you have, let's say, you have a surface and you have a normal vector. Yeah. This is a two-dimensional surface. If you compute the divergence of this, something we call that the mean curvature. It will tell you the curvature in the whole direction. It's a trace of the second fundamental form, the whole direction. And it's a minimal surface when the edge is equal to 0. Okay? For surfaces with the curvature, the mean curvature is 0. We call that the minimal surface. This one. And there are critical points of the area function. So if you have an area the domain, and you make this parameter of t, and if you compute the roots of here, it will be the size. So there are critical points of the area function.
I just want to make sure I understand this epsilon. So the thing in parentheses, you can make epsilon so small that that's as close to 1 as you want. So the only reason you wouldn't do that is because the epsilon also appears in the
Here,
in the
make
harmonic
that one
volume.
large.
There's some trade-off.
Yes,
Okay,
yes. And as a result, you don't get this condition for arbitrary domain select. Okay, let's look at the application of this result of the condition to the size of the extra dimension. And for that, we select a very special case of high dimensional gravity. So it's Kuhn-Klein theory. So Kuhn-Klein theory actually originated from the work of Kuhn and then later compactification by Klein. And the idea was simple. So look at the 5-dimensional vacuum equation and then assume the symmetry direction and then break down or do a reduction argument with that symmetry of the Einstein equation. The beautiful part is you end up with a system of equations. Those system of equations is the coupled system of Einstein-Maxwell plus a scale. Okay, so here we have a 5-dimensional space-time, and we assume the metric has the following structure. Okay, and alpha here is a fixed constant. Note that the bold G here, it's a metric of the 4-dimensional space-time. Okay, and the Z coordinate in this metric is the parameter of the circle direction. So what we have in our mind is as follows. Here is this. So we have a 4-dimensional, and 3 on 1 and G4. This, let's say, it's a time direction, and this, let's say, the space direction. And you assume that at each point there is a circle. So you get a 5-dimensional manifold. So this is your M4 on 1 and G4. Okay. So the one form here, A, is actually, it's a measure for the twist of the S1 bundle, this S1, over this space-time. And also you can geometrically, it's determine the connection of the U1. Okay? And what is phi? Phi is a function of the manifold. Physically, they call that a
When you
dimension.
say twist, you mean a binding number? You say twist.
Oh, twist is like, have you heard of like a Mobius strip?
Yeah.
Yeah, okay. So you can have S1 times, the interval. You can have S1 multiplied by interval. get a cylinder. You can have the Mobius string that has a twist. That has a twist which you can't actually see that. But there are other ways to compute this. You can say the curvature in that direction.
It's not the winding number.
And the circumference of this one, it's actually 2 pi L, which L is related to the phi. Okay, this is our setting. Now, if you look at the Einstein equation, if you break it down using the symmetry, you will have one part which is the Einstein-Maxwell and coupled with the scalar T. Okay, and here the F is the dA. Okay, it's played the role of. It's a curvature of this one bundle, but in physical sense, it's the electromagnetic field. Okay, so you have an electromagnetic field which is related to the curvature or the twist of this one bundle. Now, I want to consider initial data set, so I look at the hypersurface of constant time slice here. So this is a constant time slice. It's omega g and k. It's my time direction. So at each point, also note that it's like 5-dimensional picture. Circle. Now I can define electric field and magnetic field in the usual sense, like the contraction of F in that direction and star F in that direction. And then the initial data set for the Einstein-Maxwell scalar field, it has the following mu and j. Okay? It will be in terms of the phi, which is related to the size of this one. It's related to the twist or the curvature of this one. Okay? And here, and the phi is the rate of change in the direction of n. So here, n is this direction, time direction. Now, I define some characteristic constant, and it's normalized to be normalized to be like a length, and then the first characteristic constant depends on L, or the circumference of this one bundle, and also the twist or the curvature. The second characteristic constant depends on the rate of change of the circumference in direction, in the spatial direction, and also in the time direction. Now the theorem is as follows. This is a joint work with Fourier and Pedro. It says if at least one of two characteristic constant of initial data set of the Einstein-Maxwell scalar field satisfies the richness condition, then there exists a apparent horizon. Okay. Now I will skip the proof. It's used the Hooke conjecture, but I want to show you a consequence of this theorem.
Wait, just before you go on, so phi appears as a parameter, as a field that you specify in the form of the metric.
Yeah.
And if phi is like equal to say 1 or something, you just get Einstein-Maxwell on the 4-dimensional.
Phi cannot be the way it shows up. It's like e to the.
Right.
So if phi is equal to 1, phi cannot be equal.
So if phi is 0, if phi is 0. Yeah, but if phi is equal to 0, then you just get Einstein-Maxwell.
Yes.
Okay.
But what does it mean? Let me go back.
So phi is just a field that lives in the S1 direction. It's just some field in the S1 direction. Yeah. Okay.
Field on the manifold. It's a function of the manifold.
Right. Okay. Yeah. Okay.
So let me go to the consequence of that to cosmology. The size of the extrapolation. So if you look at the entire universe as our domain, select the our domain here is the entire universe, and we want to select the initial data set for the entire universe. We know the observable radius of the entire universe is 10 to the 26 meters. Okay? This is based on observation. And also we know that the universe does not exhibit any known topological features. And that means if you look at the constant time slices of the universe, they can be modeled by the constant, simply connected constant curvature, manifold. It could be either like, a street or a ball, a flat ball. Okay. In either of these cases, when you use this radius, when you use the notion of volume, you get 10 to the minus 19. You get this constant.
What's
And-
little L though?
L is a parameter of length. You can say it's like.
But how do you choose it?
Oh, it's the one that actually it's like it's the meter scale.
Okay, it gives you the correct unit. When
Yeah.
you write out the Einstein equations,
Yeah.
it gives you the correct constant.
Yeah.
I see. Okay.
And our theorem converts to this one for the universe. You have initial data set and you assume the universe actually covered with the line. That's it. If one of the characteristic constant is bigger than 10 to the minus 19, then a black hole must form if the concentration of geometry or richness of the extra dimension. So there are too much extra dimension. And the place which has too much extra dimension, that should be behind black hole. Okay, so what does it mean if I fix the twist and I say the curvature of the twist is like generically up to some numbers, like 10 to the minus p. Okay? Then the first inequality, you want to get them 10 to the minus 19, will lead to an inequality for the average of the circumference. Okay? And it says as long as you have this condition, then a black hole will form. So then this means that there exists a black hole due to the excessive average size of the extra dimension. So
is this a black hole on the 5-dimensional manifold or a black hole on the 4-dimensional?
Four-dimensional manifold. But there is a mathematical result which says if there is an apparent horizon, the Klein theory in the 4-dimensional, there is a 5-dimensional too. On the other hand, it says that, let's say here, there are huge circle with a huge circumference. Okay. If you take the average of that and it's bigger than the 10 to the minus 19 plus p, assuming the twist is generically like 10 to the minus p, over in this initial data set, then here there's a black hole. And this guy must be behind black hole. It's not observable. Yes.
So as the universe expands and it's not beyond the Hubble horizon, that's greater volume. Will there be larger extra dimensions? Or?
So that's the thing. If the I will exactly just 2 slides. If the universe expands, the radius will expand. Threshold will be smaller, so it will be almost impossible to detect this radiation. Because the threshold will be very, very small, then it will be all up to the Planck size.
What is the systematic dependence of the radius of the 4-dimensional black hole on the size of the extra dimension? So how big will the 4-dimensional black hole be?
Well, you don't know that.
Oh, we don't know. We don't know that. We don't know that estimate. There is a theorem in the Shane and Yao that they have also estimated that, but we did not compute. So if you use their result, we can get an estimate. Okay? But we use directly the Hooke condition, but we can't use their result. Note that this is mathematically is rigorous in the sense that you can do everything with the Shane and Yao result, with our percent result, and you can get this. And what else? If you assume the lengths of this circles, actually generically it's like up to 10 to the minus p, and assume again one is bigger than 10 to the minus 19m, then you have this inequality, which this inequality would tell us if you have too much.
But these API, whatever, those are not unique, right?
Oh, they can be different in different places. The claim is when you have a very large one, the very large one is behind black hole. It's not visible.
But if the black hole is as big as the observable universe, then the dimension.
No, black is not as big as the observable universe.
But you said that you didn't have a good estimate of the size of the black hole.
Oh, we don't have a good estimate, but we cannot conclude it's a synthesis of the universe.
Yeah, it's still of the order.
But you can predict that,
Okay.
right?
Yeah. It's doable if you use the result of Shane and Yao. You can have an estimate here. How big is that? So if you have too much twist of these guys, if these guys has too much twist, it's like a Mobius strip. You have too much twist, then that too much twist must be behind black hole too. Now what else? If you have a phenomena that's in either of these directions, the rate of change is too fast. It's like get really large very fast from one point to another, or in this direction. the same thing happen, then that should be also behind black hole. That's this characteristic constant. And now we come back to your question. So if you go back to the early universe, the diameter was small, so the threshold was large, and the extra dimension was actually visible. And if you go to the future, the radius of the will be large, and the threshold will be very, very small of the Planck size, and it will be impossible to detect the extra dimension. But to make actually the number more physically relevant, there is, if you look at the literature and we check that the length scale that they hold in LHC right now, it's up to the 10 to the minus 18. And they did not detect any kind of indication of the extra dimension.
This threshold is again a time-dependent threshold size, right? So if the 10 to the minus 19 for today,
Yes, if you go to the future, if the radius expand, then the threshold will be smaller and smaller.
And these extra dimensions are specifically for 5D Lucid line like kiloton.
Yeah. This is the 5D Lucid line theory. So you may ask, okay, if the universe does not govern with the Lucid line, it's governed with the string theory or any other theory, and you claim the same thing. And the answer is actually, if you change the matter content, or if you add a cosmological constant, same thing hold, we check that. But if you change the theory, in different theory, we expect the same thing will hold, because the technique is robust. As long as you can find the lower bound of the mu minus j in terms of the geometry of the extra dimension, and as long as that die is big enough, you get a formation of black hole. Maybe it's not in terms of the circumference, maybe it's in terms of the other way to measure the size of the extra dimension.
so at the radiation matter equality or the surface of glass scattering, so what sort of cosmologically significant efforts, what is the size? Have a sense.
Oh,
of
yeah,
the
it did
threshold
not
ever-
compute it. It did not, but that's like
I think you want to do it for the surface of glass scattering, because if the size is actually getting smaller, I mean, is there a sweet spot somewhere?
Yeah.
Radiation matter equality is one interesting cosmological time spot you want to do it for.
do we know the radius in each of these?
Yes, of course.
Okay. So
Just from the age of the universe, you can
Oh.
actually calculate it.
I see.
Using an underlying model, you can calculate the
I see.
particle horizon and that.
That's very interesting. Sure. We'll try to.
And of course, black holes are dynamical objects. They could evaporate, they could merge. So if you needed a horizon to hide an extra dimension at some point, what if the black hole evaporates? Yeah, it's going to take a very, very long time to see the black hole process like quantum radiation. But will these extra dimensions become visible if suddenly you get to a point where all the black holes in the universe disappear?
This is an interesting question. You need to know the evolution of the initial data set to answer this question. This is at the constant time. I'm just saying there is apparent horizon. The apparent horizon exists. So
And if it could be hiding an extra dimension, is there any way to project what would happen if you get some process to get rid of that black hole?
it's possible. I'm not sure. So,
Or would it have to? I mean, is there a way to unveil this dimension by some of the black hole dynamics? Because black holes, they're even if your theorem says that you have to have a black hole at one time, the black hole would disappear, and I guess what would happen to the dimension?
okay, so that's like is it also related to
I feel like that's a question for Andy, not for Aghil.
okay.
Well, let's thank our speaker. We had loads of questions during the talk. Are there any final questions or remarks people would like to ask?
No. The initial data is a three-dimensional. In the theory we started with, we assumed that the universe governed with the Lucid light. So you can change that theory to any string theory you want, and then apply the same step and find the threshold and find your measure of the size of the extra dimension. So the level, the level of the study is a three-dimensional initiative. It's completely classical.
I think a good way to express this work is that it's an argument that tells you that if you're in the classical regime, so you have a classical theory, everything's classical, then if you have these extra dimensions that are very, very large, then somehow they are going to contribute to enough energy density so that actually they end up getting hidden by a marginally out of track surface or a black hole, as you can say.
Yeah. There is like a.
We already have some good sense of energy density. For this theory to apply, was it fine to be able to just factor through that stuff we all know?
So here in the equation that we have is starting with the vacuum bidimensional, and the only type of energy in the three-dimensional level are coming from the geometry of the three-dimensional. There's no cosmological constant. But if you include it, it doesn't change the result. Contribution is more the positive side.
We do experiments here and measure so that's also consistent with
Yeah, I have not seen that. My knowledge of the like street video is not that much, but I have not seen the study that I they just look at like different matter there actually they do the reduction and in four dimension they see something beautiful. It will show up at those 50%.
Does this work on the archive?
This
Most
one
recent
is
study?
actually, yeah, this the second part. It's published.
All right, let's thank the speaker again.